we continue on with our examination of Wi-Fi physical layer alternatives. Now, these come in different amendments to the base Wi-Fi specification, and it should be added that these are optional. So not every Wi-Fi device needs to include support for all of these physical layer alternatives. However, from a practical market point of view, if you're just going to build products that use some of the less powerful physical layers, let's say 802.11a and b only, your market share is not going to be doing very well because people are looking for the more recent amendments. However, having said that, you can find products out in the market that might not support the latest. So maybe you have products that go up to 802.11g or products that go up to 802.11n and not to the latest, which currently is 802.11ac. Why is that? There are two reasons for that, at least, and one of these reasons is that it's more costly to include the most recent, latest and greatest physical layers. So things like 802.11ac are more complex, the signal processing is more sophisticated, you need corresponding hardware to also handle that. And for some people, the alternative, which is cheaper, which is to go with just, let's say, 802.11g or n, can make it attractive to just limit themselves to something like that, 802.11n, for example. Because maybe they don't need gigabit per second speeds, maybe a few hundred megabits per second with 802.11n, that could be sufficient for their purposes. Another reason why some products would be still not going with the latest, maybe 802.11n only, is that sometimes when the latest and greatest physical layer alternative is being finalized, it might not yet have been officially ratified by IEEE Standards Association, but already vendors might be making so-called pre-standard products because most of the features would already be known and specified. It's just a matter of ratifying, and there might be some small tweaks towards the end. Now, these pre-standard products can be a bit risky in the sense that they might not be fully optimized or fully compatible with the final standard that actually comes out eventually. But for some people, they might not want to wait. They might just go with one of these before the final standard emerges. So continuing where we left off, we were looking at 802.11n. And as I mentioned, it has a greater throughput than earlier physical layer alternatives, things like 802.11g. And it builds on the success of 802.11g. It introduces certain innovations like allowing wider channels, like 40 megahertz channels, and then things like MIMO with multiple antennas on both sides, allowing multiple streams of data at the same time, and thus resulting in greater throughput. It operates in both the 2.4 and 5 gigahertz bands. As you might remember from the previous discussion, there are some benefits of going with 5 gigahertz because it's not as congested as 2.4 gigahertz, but the radio range is not as far as 2.4 gigahertz. However, starting with 802.11g and then more so with 802.11n, because of the increased congestion at 2.4 gigahertz, 5 gigahertz just becomes more and more attractive. So at the same time, the cost of dual band radios was decreasing by the time we get to 802.11n, so having something that operates in both of these bands becomes more and more attractive. Additional features like DFS and TPC as well. This opens up more channels in the 5 gigahertz band. DFS is dynamic frequency selection. Anyway, because of various hardware advances, 40 megahertz was no big deal compared with 20 megahertz. And so there's not much more spectrum in 5 gigahertz as we see here, 400 megahertz more spectrum. And this is generally the best way to increase capacity in a wireless system when you throw more spectrum at it. All other things being equal. So by 2007, 802.11 was everywhere, and there's something that which happens every 5 or whatever some certain number of years. Then the 802.11 amendments that have been published in the past few years would then be rolled into the main specifications. So, for example, 802.11a, b, d, e, g, h, I, j, all of these got rolled into the base specification, and in the 802.11 2007 revision. So then officially now we shouldn't be talking about 802.11a, 802.11b, e, and 802.11g and so on, because they are actually part of the base specification. But for convenience and out of habit, people still do refer to these 802.11g, etc., rather than the corresponding section in the base specification. Similarly, when 2016 2012 came around and 2016 came around, then additional amendments were rolled into the base specification. So, for example, you might be interested to know that 802.11n now is rolled into the base specification in 2012, and then the latest and greatest of these higher and higher data rate physical layers, 802.11ac, was rolled into the 2016 revision. So technically, we shouldn't be speaking about 802.11n or 802.11ac anymore, but the corresponding sections in the base specification. But you look everywhere on product specifications and so on, you will still see these around. Then going beyond 802.11n, talking about 802.11ac, because there were these different new use cases for Wi-Fi needing even higher throughput than before. I mean, things like HDTV were becoming more common. So there's something called very high throughput that is, well, 802.11ac. Well, it's higher throughput, very high throughput compared with high throughput in 802.11n. Besides the 20 and 40 megahertz channels that we find in 802.11n, there are also 80 megahertz channels that are added in 802.11ac, plus some optional support for even wider channels going up to 160 megahertz. And there's additional other technology innovations that were added. So you have, for example, modulations like 256 QAM, quadrature amplitude modulation. So this gets you up into the gigabit range. But this is not where it ends, because 802.11ax is around the corner. It's coming within a couple of years.